morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 11, that is the cyber physical layers in distribution system. Till the last class we have seen that what are the mediums we are using, what are the problems with them, how we can mathematically model that non-idealities inside an optical fiber and the PLC wired communication mediums. And today we will see the actual implementation of those models. We have seen the OPF techniques, right. So, now we will see how this OPF techniques has been hampered or has been affected, because ultimately we are solving OPF after getting all this data. So, how these OPF techniques will be affected by all these communication non-idealities. To check this, the ideal platform with them will be a cyber physical co-simulation framework. Okay. Now, what is this cyber physical co-simulation? So, before going to that, first we will see that what is the need of this cyber physical co-simulation system. Okay. The need of the cyber physical co-simulation system will be field deployment and transition to hardware. Before going to actual hardware system, first we have to see whether our algorithm or whatever techniques or whatever communication infrastructure we are going to imply or deploy, that whether that is capable to do or not, that is capable to handle all the situations or not. So, before going to field deployment, we have to do the co-simulation. Then simulation and analysis of communication systems impact on the algorithm performance. So, whenever you will design an algorithm, let us say there is a large distribution network, okay, and then you segregate it into multiple areas, let us say 4 areas, and then exchanging the boundary values. That is what we have done for distributed OPF. So, you have developed it, you are relying, the distributed OPF relies on the neighboring values, neighboring informations. When the neighboring information will come, depending upon that, that will respond. But that means it is a highly dependent, its performance is highly dependent upon the performance of the communication system as well. If your system has high latency or the packet loss is happening, that means you will not get your neighbor data, and if you do not get your neighbor data, then your algorithm will fail. So, before doing that, it requires a co-simulation of power, communication and the control system, right. So, what is the layout of a cyber physical co-simulation? It has mainly 3 layers. First layer is the physical layer, simulates the behavior of the electric grids by modeling the network resources and the grid edge devices, and determine the power flow, voltages and the other operational dynamics. Okay. What does it mean? You actually model your power distribution network in that platform, that may be OpenDSS, GridLAB-D or any other real time network simulator. So, that will solve, actually whenever we designed the OPF, we have seen we did SOCP relaxation, we did SDP relaxation, we did linearization. So, that means we are deviating from our actual nonlinear model, though we have theoretically proved that those models are exact, but whether they are exactly giving the same results of that nonlinear model or not, that we can check from this softwares, because they solve the nonlinear power flow. So, by designing that model or the network in the OpenDSS or the GridLAB-D model or module, that will solve the exact nonlinear power flow by executing the decisions sent from the control layer. That means, whatever you have decided or the control decisions you have derived from your OPF problem, or let us say planning problem or any kind of optimization problem, what will be the impact of that problem in the actual network, that you can design by this physical layer. Then you have cyber layer, mimics the different communication protocols and communication network for realizing the data transfer between different control agents and between control and physical layers. That is acting as a medium between your control and the physical layers, because the control layers will send the control decision and that will reach to the physical layers through the communication infrastructure. So, the cyber layer, which is designed mainly at the Mininet, NS3 or OMNet++ softwares, that will emulate the real world communication behavior. You can give their latency value, you can give their data rates value, you can give the packet drop probability, you can give the actual cyber threats, you can design the cyber threats also in that communication mediums, and you can emulate those situations beforehand. Okay. Then you have your control layer, that is the actual where is your algorithm is, your OPF algorithm is. So, that will processes the data from the physical layers, perform the computation like OPF and sends control signals to the physical layer. Okay, that is generally a code, that is either C code or C++ or Python or MATLAB or Julia, any kind of code, okay, which is compatible with your physical layer software and your communication layer software, that has to be compatible. Purpose: simulate the different network management algorithms and test their efficacy. Now, you have three layers. You have one physical layer, this is your physical, this is your communication or cyber, let us say, and then you have your control. So, you have three distinct layers: physical, communication and control. So, there has to be a agent who will make or will make the possible of the shaking hands between these three layers. That means, the data has to be transferred from control to cyber and then from cyber to physical, then in the reverse way physical to cyber and cyber to control. So, there has to be one interfacing tool between, because you wrote your control algorithm in the MATLAB or let us say Python, your cyber layer is in NS3 and is your control layer is in OpenDSS or GridLAB-D. So, all three are different platforms. So, to synchronize these three platforms, to proper data transfer between them, you need an interfacing tool. So, that will ensure the time coordination, that whenever you are sending data from physical layer, instantly without having much delay, that will be transferred to your communication layer. And from their communication layer, when it will reach at the control system layer terminal, that will be instantly that will be transferred to the control algorithm. So, there has to be one agent sitting there. So, that the work of that agent is to time coordination and synchronize the data exchange among these three layers across the time steps in the co-simulation. So, that is normally done by HELICS, which is hierarchical engine for large scale infrastructure co-simulation. It is a very well recognized co-simulation tool and Mosaic application programming interface. So, this is the overall layout of a cyber physical co-simulation. You can see you have a physical layer where you actually have a grid structure, distribution network or any transmission grid also you can have, but we are focusing on distribution network. So, distribution grid, physical layer, then you will have a cyber layer corresponding to the each node, okay, where this physical layer data will be transferred to the cyber layer data. And then you have the control layer, let us say this area is controlled by one control center and this area is controlled by another control center. So, this area is connected with one control layer algorithm and this layer is connected with the another control layer algorithm. So, few data you can even send directly from the cyber layer to the control layer. So, your control layer will have the optimization algorithm centralized and distributed as the input. Your cyber layer will have the parameters like the bandwidth, latency and the protocol like wired or wireless. If it is wired, it is PLC or optical fiber, that protocol. You have selected distribution system and the physical layer will have the actual distribution system, whether it is IEEE 13 bus system, 123, 34, 33, 69, which kind of data bus structure you are using. Then after simulating, you will get the output and you investigate the quality of service parameter. You see how much is latency, total latency of the system, how much total noise it is incurring. So, those things you see and check whether that QoS limit what you have studied, there is a standard that how much QoS we can get for every application, whether that QoS limit is met or not. If it is not met, then you have to update the data transport parameters. That means, you have to change your parameter, you have to change the protocols, you have to change the length of the lines, you have to update them, or if it is yes, then note the results. So, we will see one example of a cyber physical co-simulation framework, which is the HELICS-based, which is developed by the Pacific Northwest National Lab, USA and the Washington State University, and that is mainly used by cyber physical co-simulation framework based on HELICS, considering the three layers. So, at the Python layers is used for the control system, NS3 is used for communication network and GridLAB-D is used for physical network. So, you can see the network architecture is at the GridLAB-D, your communication network is at the NS3 and then OPF algorithm is at the Python, and they are integrated or interfaced with each other with the help of HELICS. The interaction among different layers are performed in a closed loop manner. That means, all the inputs and the outputs will be sent to the its corresponding layer. That means, your physical will go to the communication, communication will go to the control, and then the reverse back as well. That is called the closed loop architecture to evaluate the performance of the centralized and the distributed OPF algorithms. The programs in these 3 layers run in parallel. So, that is how you will get co-simulation. When 3 of them will run in parallel, it is not like a serial that first your control will come, then your cyber will come, then your physical. No, continuously everyone is working, but because that is your real life scenario. It is not, no one waits for another layer to get the input. Whatever result it will get from the input, like control layer, communication layer will start acting. Then in the meantime, physical layer is giving the feedback of the data to the control layer. So, that data is also be processed in the control layer. So, it is a in parallel process, it is not a serial process. So, what is GridLAB-D? GridLAB-D is a power distribution simulation tool used to model the overhead lines, underground cables, load, transformers, regulators, meters, residential customer PV batteries. You can model everything there. So, GridLAB-D is developed by Pacific Northwest National Lab in collaboration with the industry and academia through the funding of Department of Energy, US. So, you can see the GridLAB-D code from this link. So, this is the architecture of your detailed architecture of your co-simulation framework, where you have a physical layer, and every physical layer where you want to control or you want to take the data from, that will be represented by these devices. Like it will be a meter, or it may be a DER controller, or it may be a storage, any kind of architecture from where you are fetching any data, okay, that will be generated by this device 1. So, there we are modeling it as an IEEE 123 bus system segregated into 4 areas, 10 nodes, 150 kilowatt 3 phase inverters for 4 quadrant operation. That we have already did with this example in our OPF. Now, we are implementing the same example in our cyber physical co-simulation platform. So, here is a local device controller that is coded in the Python. It is a Python script. So, receives data from the GridLAB-D and reformats them to for the controller use. That means, it will be sent to the controller or the Python, interprets controller commands and relays them to appropriate devices with the GridLAB-D. That means, it is connected properly with the GridLAB-D actual devices, which is being modeled in the GridLAB-D. So, Python will, that coding of this local device controller will be coded in the Python. Then you have the cyber layer that will take at the controller, like each and every area has been divided. So, this is one area controller, this is one area controller, this is one area controller, and this is one area controller. And with the help of NS3, the communication links have been established between the area controller and the actual meters or your DERs, where you need to send the control decisions. Your meters will sense the device voltage and the power flow, and your control will be sent to the DER. So, depending upon that, area 1, area 2, area 3 and area 4, the communication architecture is defined. So, you can see that from this architecture, that if this is an area 1, it has a control architecture. So, he has to be connected with this 23, 30, 15 and your utility grid. So, you can see that connection is there. So, it is connected with 30, 23, 20, 15 and your utility grid, and also it is a distributed. So, it has to be also connected with your neighborhood controller as well, because you need to send the data exchange the data for the distributed OPF, and similarly area 2, area 3 and area 4. Then there is a controller, or actually where your algorithm is running. So, that will take the data for all the time steps you are trying to run, like for how many time steps you are trying to run your OPF, and that will get the data from the helix. Algorithm will be run and dispatch functions will be sent and receive and store message data. That means, it will store it and then it will run the algorithm, and then if it is done, then check whether it is a end time. If it is not, then it will repeat the process. If it is, then it will terminate and finish the process. So, all these 3 layers will be correlated, or will be the data synchronization has been done with the help of Helix platform. So, we are doing some assumptions for doing this cyber physical co-simulation. First assumption is that the communication links within a particular area are ideal. That means, there is no problem when it is the communication, because there are small communication links. So, we normally assume those are very ideal one. The non-ideal communication scenario only occur between 2 neighboring distributed controllers. That means, when there is if we go to this two architecture, so these communications are your ideal communications. Only the non-ideality occurs to this communications, this one, this and this one. Okay, so we have three connections in between, so and this one as well. So this is your non-ideal communications. A local distributed controller of a particular area is placed at the bus location where from the LDCs of that area the lowest distance. That is also favorable. You do not want your communication mediums to be very long. So, normally we put the substation in that place where the electrical distance or the communication distance between different control agents or communication agents are smaller. So, that we have chosen one assumption. The length of the communication channel between two nodes is the same as the length of the power line, and the communication route from one node to another is the same as the power line. So, that is an assumption that power communication line also follows the same route of the power line. The information exchange happens synchronously in every second. Okay. So, this is the physical layer architecture where we have taken this 4 area IEEE 123 bus distribution system, which base is 100 kVA and base voltage is 4.16 kV. It has total 10 3-phase DERs or 30 PVs, single phase at each bus. Their rating is 50 kilowatt and their inverter rating is 60 kVA. The simulation is done for only one time step, that is only 1 minute, to show the effectiveness of the proposed distributed OPF over centralized existing distributed, that is the ADMM algorithms. Okay. Then the load demand for the entire network is total this much, that is the base load condition we have considered. So, there is a cyber layer, depending upon all the assumptions it is placed that the area controllers are at for 1, 2, 3, 4 areas are at the buses 20, 59, 42 and 69 respectively. The length of the communication lines that has been calculated with the help of the electrical distance, the power line distance between the two nodes where actually your this communication these controllers are placed, depending upon that this is your distance. The communication medium is modeled in NS3 and having a data bandwidth of 10 kbps. Point to point connection or optical fiber and PLC connection, that means the wired connection is simulated in this case study. The data sharing is happened after every second. Every second we are sharing the data. The NS3 simulation routes packets through the network using global centralized routing. GCR is based on the open shortest path first, that means it will send the data with the shortest path distance. Protocol, a type of interior gateway protocol. Okay. Using GCR, packets are routed according to the shortest path algorithm. So, that means if you want to send from this here to this here, it will always take the shortest path, not this path. Let us say it will take this one, it will never take here to here or here to here, then here, then here. Okay. It will not take this longer path, it will always take the shortest path to send the data from one link to another. So, what are the case studies we have considered? First one is the topology oriented, that means whether it is a direct topology, that means your communication nodes, how they are connected, star topology or circle topology, bandwidth, if it is a low bandwidth or high bandwidth, then noise, Gaussian or impulse, then delay, deterministic and stochastic. Okay. Then evaluated cases is for the loss minimization and noted the convergence curve, optimal values, worst solution time and success rate. So, this is the same loss minimization algorithm where we are trying to minimize the total 3-phase losses by controlling the inverter reactive power output and taking the linear power flow model. So, it is the same QLP formulation. You can replace it with that Pij phi square plus Qij phi square, this multiplied with the Rij phi. We know this formulation, right. We solved the multiple OPF problems with this example. So, first case study between your centralized OPF, your vanilla ADMM and your NAP based distributed OPF. And we have noticed that for the ADMM, voltage, power and the dual variables are the sharing data. For NAP, we know that the upstream network will act as a voltage source for the downstream and downstream network will act as a load for the upstream. So, this is the convergence plot. You can see that obviously the COPF will give you the convergence fast and that will be done within solution time, like we do not take this solution time, because normally it is a one shot solution, it is not an iterative process. But the load final kilowatt value or the loss value is noted, which is actually your optimal solution. So, we will see whether ADMM or NAP is obtaining that solution or not. So, with the ADMM we can see that within 1 minute it fails to converge to the point. Okay. So, that validates that what we claimed before as well, that your ADMM, your NAP is faster than ADMM from the cyber physical co-simulation, where we are using a proper cyber layer as well, we can see the NAP is better than ADMM. Okay. And it converges within 8-second time, whereas ADMM does not even converge, it stays at this higher load value, loss value. So, for NAP, convergence is achieved within 4 communication rounds, and convergence is guaranteed for NAP algorithm. With this, now we will study the performance of the NAP algorithm only for different case studies. So, first we will see the different communication topologies. This is your direct connection, that means whichever is connected. This is your C1, this is your area controller. It is only connected with this DERs and this meters. Similarly, 1 is the neighbor of 3. So, 3 is connected with its DER and its neighbor. Then 1 is connected with C2 to second area as well. So, this is a connection, then C4 as well. Now, if we revise this connection and we say that everything is connected serially, so in a circle manner. So, this is the circle architecture. Then you can go star, that everything is connected, that is a centralized, you can say, communication, star connection, where all the things are connected with only single point, let us say with the main substation communication point. And then you have a linear, that means C1 is connected to C2, C2 is connected to C3 and C3 is connected to C4. So, total 4 architectures has been considered with a bandwidth of 3 kbps and 4 different network topologies, and it is run for 2 minutes time interval. So, this is the solution. You can say that for the first minute the DER power output is fixed to 100% and then reduced to 90%, and we can see that it taking the your case 2, that means your circle, that is taking the highest latency in the system imposing. So, if your structure is having a circular structure, your data, though it is not your communication medium delay, it is only the latency due to the communication architecture or infrastructure architecture. So, if you see, if you make it circular, then you will always get a low, highest value of latency, that means your sending data will reach to the maximum delay value. Even same for the second minute, and the fastest one is obviously your the first one, that is your direct connection. This one is the best, and you can see the total maximum latency is only 4.43 second, and here it is 36.09, 11.76 and 15.08. So, it is increasing. For this it will be second highest, this is third highest, and this is the worst case condition. So, maximum latency for circular topology, thus maximum time for the convergence. Direct is the most efficient topology. The losses are the same, it is only the latency value which is changing with the communication architecture, and that has to be the true. Your solution should not deviate, only you will get the data later. Then communication stress, that we are reducing the communication data rate value, that means the bandwidth values from 3 kbps to 2 kbps to 1 kbps with the NAP algorithm, and 2 communication network topologies, that is for your star, that means this architecture, and for the circular, that means this bad architecture. If you do it, so ideal is marked with the star and circle is marked with the circle. So, you can see that the compared with the case, so this will be the ideal one. So, this is this direct one. Okay. So, you can see, for if you reduce the bandwidth, that means you are stressing the medium, the communication is delayed, and if you go to the circular with the 1 kbps, you will not even reach to the solution after the 1 minute. For other cases you will reach, but the thing is that it will be delayed reaching or delayed convergence, but the worst performance you will get when your communication medium is stressed, and as well as you are not allowing the most of the data to flow, and also you are telling them to flow in the longer path, take them the longer path. So, that will obviously take the solution to that point that will not even converge within 1 minute time. So, that means you are not getting a good not good, you are not getting even any convergence. Okay. Then we will see for the erroneous data transfer that we have modeled in our last class, that is with the random error added with a non-occurrence probability. So, it is normally done by algorithm by running 50 times to determine the worst possible convergence case and the average success rate. Okay. So, this is chi is your non-occurrence probability, and if we reduce the non-occurrence probability, you can see the success rate is also reducing significantly. That means, for 1, if it is 100% with 70% only non-occurrence probability, your success rate has been reduced to 52%. Okay? And the maximum solution time is also enhanced from 8 second to 20 second, that you can see from the convergence curve as well. The shoots are coming at that time when you are incurring a erroneous value, and that error value amplitude is very high. So, it always deviates your convergence to a significant value, and then again it has to come back, and that takes the convergence time more time. So, convergence the more time. Okay. Then if you vary the error level, that means that minus r to plus r, we have seen the maximum error value. If you see that if the error rate is obviously, if it is 0, that means it is ideal condition. If you increase, and if it is only 0.1 per unit more, then your success rate also reduced to almost 50%, and maximum solution time is 13 second. Then we will add the noise in terms of beat error rate, that is your values of 10 to the power minus 2, minus 3, minus 4 and minus 5. So, you can see that is also a 50 run thing, and the worst case possible convergence case, and the average success rate is noted. The higher noise cases result in some cases failing to coverage before the end of the 1 minute simulation time. So, when you go for very high value of noise, that is a 10 to the power minus 2 or 10 to the minus 3 value, then we will not even get success rate all the time. But if you see, if it is lower value, then almost the success rate is close to 100%. But if it is 10 to the minus 2, then success rate has been reduced to 70%. But the solution time, that is very huge, that is around 59 second for the worst case possibility. Even if you see the best case is also not coming out to be 8 for the 10 to the power minus 2. It is coming out to be around 18 second. Okay? That means noise also can delay your convergence time, because it is adding more and more bad data. So, if you are trying to converge, you will see that every time you are getting new updated data. So, that will force the algorithm to take more number of iterations, and more number of iterations means your solution time will obviously increase. Then come to the communication delay thing, where you will share the boundary values. So, algorithm is again run for 50 times, and the worst possible convergence curve is noted. So, the red dashed line, this lines denotes the time when the dispatch is sent to the inverters. That means, when the control, you will say that a control system is ready with the dispatch signal, no updated value is there, and it has been sent, okay, to the DER center. This blue dotted line says that your no updated value it is receiving from the downstream area, and this green says that it is not getting any data from the upstream area. So, it is a donate indication that upstream or downstream area has no update value, that means they had converged to their own possible values. But if you see, if you add the communication delay, then you can see that here already dispatch command is set. Now, suddenly some updated value has been received from the, because of the delay, that message has been not been reached to the destination during the course of time. So, it has reached after the dispatch decision has been decided. So, again upstream has to calculate, and then again has to go for a new dispatch command, and same for this downstream as well, and that we have seen for different areas. Okay. So, the ultimate communication delay, this convergence with the PLC and the fiber delays, if you see, the fiber incurs very less amount of delay, it is in the range of millisecond or microsecond, you can say. So, that is why the fiber is very good and normally used when you have a sensitive data or very time sensitive data, you have to send from the your sensors to the control center. That may be a protection device, or maybe any kind of automatic monitoring system, that data. PLC is normally used for AMI, where that data is, you can say, that can afford or that can not be very sensitive about the time of the communication. So, if you see the result with the PLC delay strong, like when the receiver is strong, at that time also it is taking almost 11 to 12 seconds to convert. That means it delayed a little bit. If it is a weak delay, then obviously it is going to 35, almost 35 seconds it is taking. So, depending upon whether your PLC receiver is a strong one or a weak one, depending upon that, we will see that how many communication delays or how much it is affected by the your control algorithms or your OPF algorithms are affected by your communication topology. With this, we have come to end of this course, and we will see that what we have studied in this course. You can see that first we have seen the fundamentals of the power distribution network, that was our module 1. Then in the module 2, we have detailed modeling of all the resources, DERs, your electric vehicles, solar panels, even the distribution network models as well, like its nonlinear model, linear models, its relaxed models, and their exactness analysis we have did in the module 2. Then module 3 is focused mainly on the graph based solution, which is a DER integrated. If you are integrating an unbalanced DER with your distribution network, then how you can solve your the problem, load flow problem, with the help of a graphical method. Then module 4, we have derived the optimal power flow algorithm, that is a centralized and distributed algorithm, multi-period of OPF formulation, and also as well we have quantified the uncertainty in our different kinds of DERs associated with it. And then we have checked that how you can incorporate those uncertainty models in your OPF, existing deterministic OPF models, and change them to a stochastic OPF problem. Then distribution network reliability studies, what is, how the reliability can be restored, what are the impact, like what are the effects or what are the causes which can degrade the reliability of a system, that we have studied in module 5. Module 6 focus on the T and D coordination, that how the DSOs will bid to the market or how the transmission network reacts to the distribution network grids and how they will be coordinated and they reach to the consensus, that we have studied in the module 6. Module 7 focused on the artificial intelligence enabled control of the distribution network, that how we can use the supervised learning, unsupervised learning, or reinforcement learning for controlling your DER inverters to forecast the DER power outputs, EV management, storage management, your load appliance management or appliance classification to application for the DSM and the demand response analysis, that we have studied in the module 7. Then the fault analysis and the distribution network protection, that how if it is a DER, then what are the impacts of the DER on the existing protection services, that means the overcurrent protection or distance protection, and how the AI oriented protection is good or the fault classification is good and fast acting. Then we have seen the outage management system, we have seen the fault ride through analysis in that module. Then the resiliency analysis is explored in the module 9, where we have learned that what kind of hazards effect we have on our distribution network and how we can mathematically model them, what is the long term resiliency, what is the short term resiliency, what are the methods needs to be adapted to make your system more resilient, how you can model it, what is the resiliency matrix to quantify the level of the resiliency of a particular distribution system. And also we have seen how we can see the effect or how we can see the impact of the cyclones or the extreme weather events and the wildfires in the distribution network operation. Then distribution network automation and restoration studies we have studied in module 10, which is mainly focused on your ADMS, your smart meter data, then restoration strategies and your network reconfiguration. These things we have studied, and at last in the module 11, that is the last module, which gives you the idea that how the cyber layer or the communication layer has been modeled. Without that your nothing will work, because everything involves your data transmission. So, if there is no communication medium or communication infrastructure, then none of the algorithms of the distribution network will work. So, how this communication infrastructure is modeled, how the distribution network relies or dependent, how much they are dependent on the condition of the communication layers, and as nothing is proper, or you can say ideal in this world. So if there is a non-idealities in the communication system, so how that communication system will react, or your system will distribution network will react in response to that communication non-idealities. So with this we will end this course of the NPTEL, and I hope that this course was beneficial for you, and it will improve your knowledge about the distribution network studies. And with that, thank you so much.